Good morning, everyone, and welcome back to the physics session. So, yesterday we have seen some of the basic concepts from the chapter 2, which is the mechanical properties of the fluid. So, the last point that we were discussing it was a pressure inside a drop and the bubble. So, this pressure we can give by using this relation, which is a Pi minus P naught is equal to 2T upon R. So, this is for the liquid drop. So, P naught is the atmospheric pressure. So if you want just the gauge pressure, then we can neglect this P naught. That means we can assume this to be 0 and just we can write the pressure Pi. This is equal to 2T upon R. So this is for the liquid drop. And second equation is for the soap bubble. So its equation pressure is equal to 4T upon R. Okay, so here we have the 2T and this is the 4T. It is because soap bubble, it has two surfaces, that is inside surface and the outside surface. And for the liquid drop, we need to consider only one surface, and therefore it is 2T upon R. So this is the pressure equation for drop and the bubble. Next is the capillary action. So what is capillary tube? So tube having the bore diameter up to 1 mm and it is open at both the ends. So this is called as a capillary tube. Okay. So bore diameter is up to 1 millimeter. If this tube is deep in a liquid which wets the surface of that tube, then the liquid rises in the tube. Okay. So here you can consider water that wets the surface of the glass tube. In this case, if you dip the capillary tube, that is a glass tube, inside the water, then water it will rise up. Okay, if the tube dip in a liquid which does not wet the surface, so here example is the mercury. Okay, so for the mercury, angle of contact is obtuse, so nearly it is a 135 degree. Okay, then the liquid level it will drop in the tube. Okay, so you should remember, for the water that wets the surface, that is a glass tube, water will rise in the capillary tube, and the liquid which does not wet the surface, for example mercury, then the level of that liquid it will drop in the tube. Okay, so the first example, this is for the water. Okay, so from this level, that is the level of the liquid in the container, if we dip the capillary tube, then this liquid level will rise in that tube. Okay, and second example is the mercury. So mercury level it will drop in the capillary tube because it does not wet the glass tube. Okay, now the capillary fall or the capillary rise in the capillary tube, it is given by this equation, which is H is equal to 2T cos theta upon R rho G. Okay, where T is the surface tension. So this is the surface tension. This is the Newton per meter. Theta is the angle of contact. R is the radius of the capillary tube. Rho is the density of the liquid, and G is the acceleration due to gravity. Okay. Same equation we can use for the fall and the rise. That is for water, mercury and the water. So for capillary fall, for the liquid which does not wet the glass tube, for example mercury, theta angle is the obtuse, that is greater than 90 degree, and therefore cos theta is a negative. Okay, and for the capillary rise, theta is the acute angle, that means theta is less than 90 degree. In this case cos theta is a positive. Okay, so capillary fall, we will get the answer for H as a negative because of cos theta is a negative. Okay, so this is the equation for capillary fall or the capillary rise. So you should remember this equation to solve the problems. Okay, the next point, it is the fluid motion. So yesterday we have solved some objective questions on the fluid motion. So let us discuss some basic concepts regarding the motion of the fluid. So the first is the steady flow. So what is meaning of a steady flow? Properties of the fluid like velocity, pressure at a particular point do not change with the time. Okay. So if you consider a pipe, and suppose a fluid is flowing through that pipe, let us take the water. And if you select any one point, okay, and at this point, if you measure the pressure and the velocity at different time instant, okay, so let us take time t0, t1, t2, t3 second. So for all this time interval, pressure and the velocity, it will remain constant. Okay, so there is no variation, and this is called as a steady flow. In the steady flow, if I select another point in this pipe, we can have different pressure, okay, with respect to this point. But at this point, if you measure the pressure and velocity at different time interval, so that pressure will remain same. So this is called as a steady flow. Property will not change with respect to time. Second is the flow line. So what is a flow line? It is the actual path traveled by individual fluid particle. That is called as a flow line. Okay. So suppose these are four fluid particles or the water particles. And the water is flowing in this direction. Okay. So this single fluid particle will travel along this path. So these are the successive location of the same fluid particle. Okay. So this path is called as a flow line. Next is streamline. So it is the curve whose tangent at any point gives the velocity of flow at that point. Okay. So suppose this is the bend in a pipeline, or you can take this as an elbow. So these are the streamlines. That means fluid particle travels along this path. Okay. And if I select any one point and if I draw the tangent, okay, so this tangent, it will give the velocity direction at this point. Okay. So streamline and the flow line for a laminar flow, they are the same. Okay. So we cannot differentiate streamline and the flow line for the laminar or the streamline flow. So flow lines, streamlines are same for a steady flow, and steady flow means it is the laminar flow. Okay, what is the laminar flow and the turbulent flow? So it is the steady flow in which adjacent layers of a fluid move smoothly over each other without mixing into each other. Okay, so for the laminar flow, fluid particle will travel in different parallel layers smoothly without mixing into each other. Okay, so this fluid particle will not cross the adjacent layer. So flow will appear as a parallel lines. Okay, so this is called as a laminar flow. And second is the turbulent flow. So it is the flow in which flow pattern changes continuously. So it creates eddies in the flow and flow rate is very high. So for the turbulent flow, so we can observe the flow pattern like this, which creates the eddies. Okay, so such type of flow pattern, it is for the turbulent flow. And for the turbulent flow, the flow rate of that fluid is very high. Okay, so this is the difference between laminar and the turbulent flow. Now, this laminar and turbulent flow, we can differentiate based on the Reynolds number. Okay, so we will see what is critical velocity and the Reynolds number. So, critical velocity means the velocity beyond which streamline or the laminar flow becomes the turbulent. So, this velocity is called as the critical velocity. And the critical velocity, it is given by this equation Vc is equal to Re, this is the Reynolds number, eta upon rho into d. Okay, where eta is the coefficient of viscosity. So it is given as a Newton second per meter square. And from this, we can write the Reynolds number as Vc, that is the critical velocity, rho d upon eta. Okay, where this equation, Reynolds number, basically it is the ratio of inertia force to the viscous force. Okay, so from this equation, we can find out the Reynolds number, which is the dimensionless parameter. So dimensionless parameter means what? It doesn't have any unit. Okay, so it doesn't have any dimension. So if Reynolds number is a less than 1000, then we call the flow as a laminar. If Reynolds number is greater than 2000, the flow becomes turbulent. Okay. So based on this Reynolds number, we can differentiate whether the given flow is a laminar or a turbulent. Okay. And if the Reynolds number, it lies between 1000 and 2000, then the flow is unsteady. Okay. So unsteady means what? The flow is slowly changing from laminar flow to the turbulent flow. Okay, so it changes from the laminar to turbulent flow. Okay, so this is the unsteady flow, or we call this as a transition zone. It is not perfectly laminar or perfectly turbulent. Okay, next concept is the viscosity. So, what is viscosity? It is the property of the fluid due to which one layer of the fluid offers the resistance to the motion of the adjacent layer. Okay. So, it is also called as a fluid friction. And when the fluid flows in the pipe, generally we observe a parabolic profile, and the reason is the viscosity. Okay. So, viscosity means one layer of the fluid will offer the resistance to the motion of other layer. So if you consider the fluid is like this, layer has velocity v, then the velocity will gradually like this. Okay, so it will have the maximum velocity v, and suppose this is the stationary surface or the pipe wall or the boundary, then at this layer which is in contact with the wall, velocity is zero. Okay, so this is because of the fluid friction. Now the coefficient of viscosity, it is given by the Newton's law of viscosity. Okay, so actually Newton's law of viscosity, shear stress is directly proportional to the dv upon dx. Okay, so this is the velocity gradient. Okay, and from this tau is equal to mu into dv upon dx. Okay, now this tau is the shear stress, so which is given by F upon A, this is equal to mu into dv upon dx. So this tau is the shear stress. So we can write this shear stress as force upon area. And from this, we will get the equation as viscous force, which is a F. This is equal to mu A into velocity gradient, which is a dv by dx. Okay. So mu is the coefficient of viscosity. Sometimes it is given in the book as eta. Okay. So eta into A into dv upon dx. So this is the equation for the viscous force or the shear force between the fluid layers. Okay. Now this force actually it acts tangent to each layer. Okay. So this is the direction of that force. So if you draw this layer in a 3 dimension, so this is single layer. Okay. And this is the area of that layer. Okay. So this force, it will act on this area like this, which is the tangent. Okay. So we write this F upon A for the shear stress tau. So that A is nothing but this area. Okay. So area of the layer. And from this equation, we can write coefficient of viscosity, which is a mu or eta. This is equal to F upon A into velocity gradient dv upon dx. Okay. So coefficient of viscosity is nothing but the viscous force per unit area and per unit velocity gradient. Okay. Now viscosity, it is given as a dynamic viscosity or the kinematic viscosity. Okay. So dynamic viscosity, its unit is Newton second per meter square, or it is a Pascal second. So this is the SI unit. In the CGS unit, it is represented as a poise. Okay. So 1 poise, this is the CGS unit. This is equal to 1 by 10th of Newton second per meter square, or this is equal to 0.1 meter square, or 1 Newton second per meter square. This is equal to 10 poise. Okay. And the kinematic viscosity. So it is the ratio of dynamic viscosity of the fluid upon the density. Okay. So it is a mu upon rho. So if the question is determine the kinematic viscosity, then dynamic viscosity is given, then just divide this by the density. Okay. We will get the kinematic viscosity. And kinematic viscosity, it is expressed as a nu. So this is the kinematic viscosity. Okay, next concept is the Stokes law. So Stokes law, it gives the relation for the viscous force. So viscous force acting on a small spherical body falling through a viscous liquid. So consider the sphere and it is falling in a viscous fluid. Suppose this is the container. Okay. And this container is filled with some liquid or oil. So this is the velocity. Okay. So when the sphere is falling down in this viscous fluid, this fluid will offer some force, that is a viscous force on the sphere. Okay. So this force is given by the Stokes equation. So that equation is F is equal to F is directly proportional to eta r v, and F is equal to k into eta r v. K is the constant. Okay. So for spherical bodies, this constant k, this value is 6 pi. So finally, the equation for the viscous force acting on the spherical object is 6 pi eta r v. Okay. So where radius of the spherical bodies are, eta is the coefficient of viscosity, v is the velocity of the spherical body. Okay. So this is the final equation for the viscous force. Now, what is the application for the Stokes law is formation of clouds. Then second, to come. Okay. So we can determine the force acting on speed of the raindrops being less than that of the body falling freely with constant velocity, and to determine change with the help of Millikan's experiment. Okay, so these are some applications for the Stokes law. So in the Stokes law, you should remember this equation. So there can be question on this equation to determine the viscous force. And in the same, the second equation is the terminal velocity. Okay, so terminal velocity means when object, that is a spherical object, the viscous medium, so after some time, that is after some initial displacement in the downward direction, so this is the viscous medium, its velocity, it becomes constant. Okay, so that velocity is nothing but the terminal velocity. That is a constant velocity in the downward direction of the spherical object in a viscous fluid. So this velocity is given by the equation. It's a 2 by 9 r square rho minus sigma upon eta into g. Okay. So where this rho is the density, then eta is the viscosity, okay. Next is the fluid motion. In the fluid motion, we have one continuity equation. So continuity equation, suppose we have a pipe like this. Okay. So cross section 1 is A1 and the cross section 2 is A2. Okay. So here A1 is greater than A2. And the fluid is flowing from left to right. Okay. So in such case, the mass of the fluid at section 1, that is mass entering at section 1, it is equal to the mass entering at leaving at section 2. Okay. So this is the continuity. Okay. So total mass of the system, it will remain same. Okay. So there is no loss of the mass. So this mass of the fluid we can give by this equation, density into the volume. Okay. That is the volume swept, and this is equal to density of the volume at section 2. Okay. So this equation of the volume, it is given by, if V1 is the velocity, then A1 into V1. So A1 into V1, A1 is the cross section into delta T. Okay. This is equal to rho A2 V2 into delta T. Okay. So time instant is same, density is same. So equation we get as A1 V1, this is equal to A2 into V2. So this equation, this is called as a continuity equation. Okay. So by using this equation, if you know initial velocity, and the cross section A1 and A2, we can find out the velocity V2. Now the second equation is rho into dV upon dt. So this dV upon dt, so this is equal to dm upon dt, and this is called as a mass flux. So here dV upon dt is the volume change with respect to time, and rho is the density. Okay, so rho into volume, it becomes the mass, that is the density into volume. Okay, so dm upon dt, it becomes the mass flux, that is the rate of change of mass per unit time. And A into V, so this equation, so this is equal to dV upon dt. Okay, that is the volume upon time. So it is the volume of the fluid per unit time. Okay, next equation in the fluid motion is Bernoulli's equation. Okay, so Bernoulli's equation, basically it is the energy conservation equation. So suppose the fluid is flowing from section 1 to the section 2. Okay, so this is one conduit, or we can consider this as a pipe. Okay, now this is the datum line. So this is the datum or the reference. Okay, we can consider this as a ground. So section 1, it at height Z1, and section 2 is it at Z2. Okay, so Z1 and Z2, these are the elevations with respect to the ground. Now velocity of the fluid at section 1 is V1, and at section 2 it is a V2. Okay, at this section pressure is a P1, and here the pressure is P2. Okay, so Bernoulli's equation is total energy at section 1, it is equal to total energy at section 2. Okay, we will not consider fluid is having the viscosity, so we will consider fluid is a inviscid, viscosity is 0. Okay, so in this case we can apply the Bernoulli's equation. So what is total energy? So this total energy is the summation of the pressure energy, then velocity energy, that is the kinetic energy, and the potential energy. Okay, so pressure energy, it is given by P1 upon rho g. This is called as a pressure head. V1 square upon 2g is the velocity head or the kinetic energy head plus Z1. Okay, this is equal to P2 upon rho g plus V2 square upon 2g plus Z2. Okay, so same equation, if I multiply by rho g to complete equation, then we will get P1 plus 1 by 2 rho V1 square plus rho g Z1. This is equal to P2 1 by 2 rho V2 square plus rho g Z2. Okay, so Bernoulli's equation is this total energy, pressure, kinetic energy, and the potential energy. Okay, it remain constant. So this is the Bernoulli's equation. So you can remember this equation. Okay, and just if you multiply by rho g, you will get the second equation. Okay, so this is about the Bernoulli's equation. Now, what are the applications of Bernoulli's equation? So first application is we can determine the speed of efflux. Okay, so efflux means, so consider this is one flask or the container, and it is open at its bottom. Okay, so it is filled with some liquid. Let us take the water, and if you open this wall at the bottom, then liquid will start flowing due to gravity. Okay, so this velocity of the liquid we can determine by using the Bernoulli's equation. So this velocity, it is given by this equation. V is equal to square root 2gh. Okay, where h is the height of the liquid in the container. Okay, so this is the initial height. At the initial condition, we will get the velocity. And if h is after some time, the height h, it will start decreasing. Okay, so velocity will also decrease. So it depends on the initial height h. Now, second application is the Venturi tube. Okay, so generally Venturi tube, it is used to measure the flow rate. Okay, so Venturi tube, it consists the converging area, then there is a throat, and again the diverging area. Okay, and this converging area, it is connected to the pipe through which the fluid is flowing. Okay, so if you want to measure the flow rate of that fluid, then we need to connect one glass tube. Okay, so this glass tube is nothing but the piezometer that measures the pressure or the pressure difference, and second glass tube is connected exactly at the throat. Okay, so at the throat, the cross sectional area, let us take this a0, and here we have a1. Okay, so cross section is a0 is less than a1, so pressure will be less than pressure at section 1. Okay, so here this is the liquid height in the piezometer at section 1. At section 2, the liquid height is less than section 1. So you will get the level difference, which is the h. Okay. So by measuring this h, we can determine the velocities. Okay. Suppose we know the velocity at 1, we can determine the velocity at 2. Okay. So the basic equation is P1 minus P2. That is a pressure difference at section 1 and 2. So let's take this as a 2. Okay. P1 minus P2, this is equal to rho GH. And 2gh, this is equal to v2 square minus v1 square. This is the equation for velocity. Okay, so h is equal to v2 square minus v1 square upon 2g. So by using this equation, we can determine either the level difference in the glass tubes, that is the pressure difference h, or if h is given and one velocity is given, that is a v1, we can determine the v2. Okay, the next is the lifting of an aeroplane. Okay, so the reason to fly the aeroplane is, so you can consider, so this is the wing of the aeroplane. Okay, so this wing of the aeroplane, its cross section, so this is the cross section. Okay, so this is the streamline or the aerofoil. Okay, now air passes over this streamline. Okay, so the air at the top section moves faster compared to the bottom section. Okay, so as the velocity is maximum at this top section, it will have the low pressure. Okay, so in this region, low pressure is created compared to the bottom. Okay, and bottom, it remains at atmospheric pressure. So atmospheric pressure is greater than the pressure at the top section. Okay, and because of this pressure try to push the aeroplane in the upward direction, so that creates the lift. Okay, so this is the reason due to which aeroplane can fly in the air. Second is the blowing of the roof by the storm wind. Okay, so the wind flows over this roof. Okay, so at this section the velocity is maximum, and because of this it creates the low pressure area, and pressure at the bottom of the roof, it remains at the atmosphere. Okay, so here atmosphere pressure is greater than the pressure which is above the roof. Okay, and because of this it try to push the roof in the upward direction. Okay, and it blows off the roof. Okay, so now we will discuss the objective questions. Okay, so yesterday just I made one mistake in this problem. In a laminar flow, the velocity of the flow at any point in the liquid, the first option is does not vary with time. Second, may vary in direction but not in magnitude. Both in magnitude and the direction. Okay, so correct option is option D. So in the laminar flow, velocity of flow at any point in the liquid, so it may vary both in magnitude and direction. Okay. Okay, so now we will discuss about the viscosity. So force of the viscosity, is it gravitational, electromagnetic, nuclear, and other? Okay, so correct option for the viscosity is viscosity force or the viscous force. It is the electromagnetic force. Okay, so basically that force, it is created because of interaction between the molecules. Okay, so this layer try to slide over this layer. Okay, so this is the friction between the molecules. So it falls under the electromagnetic, that is the molecular interaction. Second question is, with the rise of temperature, the viscosity of gas increases, decreases, does not change, may increase or decrease. Okay, so when the temperature increases, then viscosity, it will increase for the gas. Okay, the reason is, for the gas, if you increase the temperature, then its kinetic energy will increase. So suppose we have one container, okay, and this is the gas inside that container. Okay, so as we heat this, it will increase the temperature, and because of this, kinetic energy of the molecule of the gas will increase. Okay, and it will increase the probability of the molecule to hit the other molecule, okay, other adjacent molecule. Okay, and that will increase the viscosity. So correct option is option A. With rise of temperature, viscosity of the gas will increase. Now viscosity of the ideal fluid. Okay, so we have seen what are the characteristics of the ideal fluid. Okay, for the ideal fluid, viscosity, it must be 0. Okay, so option is option A. For ideal fluid, viscosity is 0. The angle between viscous force and the motion of flow of liquid. So this angle is 0, pi by 2, pi by 4, or pi. So in the viscosity, we have seen viscous force is always tangent to the fluid layer. So suppose this is the fluid layer. Okay, this fluid layer, and consider adjacent layer like this. Okay, this is the velocity of this fluid layer. Now this second layer will try to oppose the motion of the first layer. Okay, as it opposes the motion, that means the force of opposition, that is the viscous force, it must be exactly opposite to the velocity. Okay, so angle between viscous force and the motion of flow, so this is the velocity, sorry, this is velocity, and this is the force. So this is pi, that is a 90 degree, 180 degree. Okay, so correct option is option D. Angle between viscous force and motion of fluid is 180 degree. Okay, next is 1 centipoise is equal to how many kg meter per second. So what kg meter per second is? 1 Newton second per meter square. This is nothing but 1 kg per meter second. Okay, both are SI unit for the dynamic viscosity. That is the mu or eta. Okay. Now poise, that is a 1 poise. This is equal to 1 by 10th of Newton second per meter square, or this is 1 by 10th of kg upon meter second. Okay. So question given is 1 centipoise. So 1 poise, this is equal to 100 centipoise. Okay. So 1 poise will be how many kg per meter second? So 1 poise is 100 centipoise. So 1 centipoise, this is equal to 1 upon 100 poise. Okay, and 1 poise, this is equal to 10 if you refer this. Okay, sorry, 1 by 10 of kg meter second. Okay, so this will be 1 upon 100, 100 into 10, so 1000. 1 by 1000 kg meter second, 1 centipoise. So 1 centipoise, this is equal to 0.001 kg meter second. Okay, so correct option is option kg upon meter second. Okay, so you should know this relation. 1 poise is equal to 100 centipoise, or 1 centipoise is equal to 1 upon 100 poise. And second relation is 1 poise is equal to 1 by 10th of Newton second per meter square, or 1 by 10th of kg upon meter second. Okay. For the next problem. The velocity of the water in the river is a 9 kilometer of the upper surface. The river is 10-meter deep. If the coefficient of viscosity of water is 10 to the power minus 2 poise, then the shearing stress between the layers of the water. Okay, so here so this is the top layer of the river. Okay, and the speed of this layer, so its velocity given, this is 9 kilometer per hour. Okay, and the river is 10-meter deep. Okay, so this is the bottom surface of that river. So this height of the layer is a 10 meter. The coefficient of viscosity of the water, so this is a mu, this is equal to 10 to the power minus 2 poise. Okay, and question is shearing stress. We have to find out what is the shearing stress. So we have the equation tau is equal to, that is the shear stress, this is equal to mu into du or dv upon dx. Okay, or simply we can write mu is equal to v upon x. So x is the height of the layer. So here velocity is given as a 9 kilometer per hour. Convert this into SI unit. So just multiply this by 5 by 18. So 5 upon 18. So this is 5 by 2 meter per second. Okay. Then mu is given as a poise, which is a 10 to the power minus 2. So what is a 1 poise? 1 poise is 1 by 10th of Newton. Okay. So 10 to the power minus 2 into 1 by 10th Newton second per meter square. So this is 10 to the power minus 3 Newton second per meter square. Okay. So we have converted velocity into SI unit, that is a meter per second. So multiplication factor is a 5 by 18. Converted velocity, viscosity, which is given in poise in terms of Newton second per meter square. Okay. Now put this value in this equation. So tau is equal to, this is mu is 10 to the power minus 3 into velocity is 5 by 2, that is a 2.5 upon x is nothing but 10 meter. So this is the height. So this is 2.5 into 10 to the power minus 4. Okay. So what is the correct option? So there is no 10 to the power minus 4. So just write this as, shift this decimal place on the left side. So it is a 0.25 into 10 to the power minus 3. Okay. And unit of the stress is a Newton per meter square. So correct option is option B, which is a 0.25 into 10 to the power minus 3 Newton per meter square. Okay. So to solve such type of problem, that is on the Newton's law of viscosity, you should know the equation of shear stress or the shear force. Okay. Then you should know the conversion of the viscosity. Okay, now refer the next problem. Dimensional formula for the Reynolds number is. So dimensional formula for Reynolds number is, as a Reynolds number, this is the dimensionless parameter. Okay. So there is no unit for the Reynolds number. It is just a constant value. So its dimension will be L0, M0 and T0. So your option is option A. Okay. Okay, next is the sphere of influence has a radius of about 10 to the power minus 10, 10 to the power minus 14, minus 19 and minus 9. So sphere of influence, so this is in the cohesive forces. So suppose this is the molecule, that is the central molecule. Then this molecule will apply the force of attraction on adjacent molecules up to the distance. So this distance, this is of the order 10 to the power minus 9 of meter. Okay. So the sphere of influence has a radius of 10 to the power minus 9. So correct option is option D. Okay, now we will discuss some questions on the surface tension and the surface energy. So first is, small drops of liquid acquire the spherical shape because of, first is of gravitational force, atmospheric pressure, then volume of spherical drop is minimum and liquid surface tends to have minimum surface area. Okay. Small drops of liquid acquire spherical shape because the liquid surface tends to have the minimum surface area. Okay. And therefore we have the spherical shape. So correct option is option D. Surface tension of the liquid, for the second question, surface tension of the liquid is due to cohesive force, adhesive force, tension in the liquid, and atmospheric pressure. So surface tension, its reason is cohesive force. Okay, attraction between the molecules of the liquid. Third question is a brush dip in a water and it is removed. The hair of the brush clinch together due to. Okay, so the reason is surface tension of the water. Okay, this is the reason the brush clinch together. Correct option is option D. Fourth is as the temperature of the liquid rises, its surface tension. So it remains same, B increase, C decrease, and none of the above. Okay, so when we increase the temperature for the liquid, then its surface tension, it will decrease. Okay, only exceptional case is molten cadmium and the copper. Okay, we have discussed yesterday. So if you increase the temperature of liquid, then surface tension, it will decrease. Correct option is option C. Okay, at a critical temperature, surface tension of the liquid is so 0, infinity, same as that other temperature, and none of the above. Okay, so correct option is option A. At critical temperature, the surface tension is 0. Okay, the surface tension of liquid is 10 raised to 8 dyne, sorry, 10 raised to 8 dyne per centimeter. So it is equivalent to, so this problem is just of unit conversion from dyne to centimeter, to Newton per meter. So we should know the conversion of dyne. So 1 dyne, this is equal to 10 to the power minus 5 Newton. Okay. So 10 raised to 8 dyne, so upon centimeter, this is equal to 10 to the power 8 into 10 to the power minus 5. This is Newton upon centimeter to meter will be 10 to the power minus 2. So 1 centimeter, this is equal to 10 to the power minus 2 meter. So this is equal to, so this is minus 5 minus 2, so minus 3. So 10 raised to 8 into 10 to the power minus 3 Newton per meter. And finally, you will get the answer as 10 to the power 5 Newton per meter. Okay. So correct option is option C. So you can note down this conversion. 1 dyne is equal to 10 to the power minus 5 Newton. Okay. Refer the next question. A needle of 0.05 meter can just rest on the horizontal surface of water without wetting. What is its weight? And the T, that means surface tension, is 7 10 to the power minus 2 Newton per meter. Okay, so here we have to find out the weight of that needle which is floating on the water surface. So suppose this is the needle. Okay, and it is floating on the water surface. So water will try to apply the force due to surface tension along its length. Okay, suppose the total length of the needle is L. So this is the force. So surface tension, its formula is T is equal to F upon the length on which the force will act. Okay, so here the force will act from this side, length is L, again from this side its length will be L. Okay, so total length is a 2L. Okay, so this force is nothing but weight, so it will balance the weight, so W upon 2L, and weight is equal to this 2 into 2L. So T is given as 7 10 to the power minus 2. 2 into L is 0.05. So you will get the answer as this is a 14 10 to the power minus 2 into 5 10 to the power minus 2. Okay. So this is 70 10 to the power minus 4. So this is equal to 0.007 Newton. Okay. So correct option is option C. So for this problem, you should know this formula. Okay, refer the next problem. A thin circular plate of radius r has a hole of radius r, that is a small r, at its center. Okay, so there is one circular plate like this. It has a central hole. So this radius is small r, and this radius is a capital R. Okay, so it is floating on the liquid surface, and surface tension is T. Then force of surface tension acting on the plate. So we have the equation surface tension is equal to F upon the total length, okay, on which the force will act. So here the total length on which the force will act. So this is the external perimeter, okay, and we have to consider this internal. So this is the total length. So the L here, this is equal to 2 pi capital R, this is the external perimeter, plus 2 pi into small r. Okay, so this is 2 pi in bracket r plus r, this is the total length. So from this equation, we will write F is equal to, this is T into L, and this is equal to T into 2 plus r. Okay, so this is the surface tension. So correct option C, T 2 pi r plus r. Okay, refer the next question. The potential energy of a molecule on the surface of liquid compared to that of the molecule inside the liquid is smaller, the same, greater, and D is 0. Okay, so potential energy of a molecule on the surface of liquid, which is compared to that of the molecule inside the liquid. Okay, so it is a greater on the surface, that is the potential energy. So if you consider, so this is the liquid. Okay, so on this surface we have some molecule, and the molecule inside that liquid. So this will have the higher potential energy. Okay, the surface tension of liquid is P. The increase of its surface energy on increasing the surface area by A. Okay, so surface energy, which is the dW, this is equal to T into dA. So this is the formula for surface energy. Okay, so just we can write this as dA as A. So this is T into A. So if you increase the surface tension of liquid by T amount and the increase of surface energy on increasing the surface area by A, so it will increase by the same amount AT. So correct option is option B. Okay, refer the next problem. Work done in blowing a soap bubble of radius 5 centimeter and surface tension of the soap, this is equal to 30 10 to the power minus 2 Newton per meter. So here surface tension is given, which is 30 10 to the power minus 2 Newton per meter. And we have to find out what is the work done. So work done or the surface energy, this is equal to T into dA. Okay. So this is equal to, for soap bubble, as it is a bubble, it will have the two surface areas. Okay. And for the sphere, we have the surface area. So surface area for this sphere or the spherical object, this is equal to 4 pi r square. Okay. For the bubble, we have to consider two surface areas. So it is a 2 into 4 pi r square. So T into 2 into 4 pi r square. Okay. So surface tension is 30 10 to the power minus 2 into 2 into 4 pi into r is 5 centimeter. So 5 into 10 to the power minus 2 meter square. Okay. So if we solve this, so this is 60, this is 240 into pi into 10 to the power minus 2 into this 25 and 10 to the power minus 4. So this is 24 into pi into 25. This is 10 to the power minus 2. This is 1. So minus 1, 10 to the power minus 5. Okay. So find out this multiplication. So you will get the answer as 1.884 into 10 to the power minus 2. Okay. So your correct option is option B. So important part is we should know this formula for work done or the surface energy. Then for the bubble, we should consider the 2 times surface area. So it is a 2 into 4 pi r square. Okay, refer the next problem. A spherical liquid with a drop of radius r is divided into 8 equal droplets. If surface tension is a capital T, then the work done in the process will be, okay. So here a single spherical drop of radius r, it is divided into 8 equal droplets. That means when we break a single drop into n droplets of equal radius. Okay, so this drop has capital R radius. So if surface tension is T, then the work done in this process. So work done when single drop is broken into number of droplets, that is n droplets. So this work done is directly given by this equation. W is equal to 4 pi r square T in bracket n to the power 1 by 3 minus 1. Okay, so n means number of droplets. So here droplets are 8. So this is 4 pi r square t. This is 8 raised to 1 by 3. So it is a cube root of 8 minus 1. So this is a 2 minus 1. So answer is 4 pi r square t. Okay. So your correct answer is option C, 4 pi r square t. Okay. So you should remember this formula. When a large single drop divided into n equal droplets. And similar to this, if you have n droplets, okay, this is the n number, they form one single drop, then the total energy W is equal to n raised to 2 by 3 4 pi r square. So here small r is the radius of the smaller droplets into t. Okay. So by using this relation, we can find out the surface energy. Okay, now next point is the angle of contact. So first question is, liquid does not weight the solid if the angle of contact is. So if the liquid doesn't weight the solid, for example, mercury and the glass, then angle of contact, it must be obtuse. Okay, obtuse means theta greater than 90 degree. In this case, liquid will not weight the solid. So in the example, can you remember this, mercury and water. Second, the wettability of a surface by a liquid depends primarily on, okay, wettability means what? Ability to weight the solid surface by the liquid. Surface tension, density, angle of contact, and the viscosity. So wettability, it depends on the angle of contact. Okay. So reason is here, first question. Next question is, for a mercury and glass, Fc and Fa are cohesive and adhesive forces respectively. Then what is the correct relation? Fc less than Fa, Fc greater than Fa, Fc equals Fa, and Fc is 0. So Fc means cohesive force. Okay. So for glass and mercury, we observe such meniscus. Okay. So here we have the Fa, that is the adhesive force. Then this is the cohesive force, which is the Fc. Here we have the tangent, and this is the resultant force. Okay. So Fc is greater than Fa. This is the tangent T. And this angle, this is theta, which is obtuse angle. Okay. So Fc is greater than Fa for the glass and mercury. Okay. And therefore theta is greater than 90 degree. So correct option is option B.
A capillary tube, when immersed vertically in a liquid, records a rise of 3 centimeter. If the tube is immersed in a liquid at an angle 60 degree with the vertical, the length of the liquid column along the tube will be. Okay. So condition given is, in the first case, the tube is immersed vertically and the liquid rise in this tube. So this height, this is 3 centimeter. Okay. Now in the second case, it is immersed incline. Like this. Okay, so when we immerse the glass tube, capillary tube, at inclined condition, the height of the liquid or liquid rise, it will remain same. So this height, it will remain same. So it will remain as a 3 centimeter only. Okay, only length of the liquid, it will increase. So along the tube, if you measure, then this will increase. Okay, so question is, we have to find out the length of the liquid column along the tube. Okay, so this vertical height, it will remain same. So it is a 3 centimeter only. So if you use the trigonometry, so this angle is given with respect to this vertical. So this is 60 degree. Okay, so just draw the right angle triangle. So this is given as a 3 centimeter. We are interested in this diagonal, okay, that is a L, and this angle is given as a 60 degree. So here L cos 60, that is L cos theta, this is equal to 3. Okay, so L is equal to 3 upon cos theta, that is a cos 60, and cos 60 is 1 by 2. So 3 upon 1 by 2. So this is equal to 6 centimeter. Okay, so length of the liquid along the tube, it will increase in the inclined condition, but vertical rise of the liquid, it will remain same. So correct answer is option C. Okay. Water can rise up to a height of 12 centimeter in a capillary tube. If the tube is lower to keep only 9 centimeter above the water level, then the water at the upper end of the capillary. Okay. So in this case, so what is given? This is the capillary tube. It is immersed in the water. Okay. The height of 12 centimeter in a capillary tube. So up to 12 centimeter. If the tube is lower to keep only 9 centimeter above. So if you lower the tube like this, so this portion above the liquid level, it is just a 9 centimeter. Okay. So condition is overflow, that is a capillary will overflow, form a convex surface, form a flat surface, and form a concave surface. Okay. So water will still rise, but it cannot overflow. Okay. So at this end, it will form a flat surface. So correct option is option C. Okay, refer this question. Flow of ink in a refill of dot pen is due to, and it is due to the option A, which is the capillarity. Second, the meniscus of liquid in a concave, sorry, the meniscus of the liquid is concave if P1 and P2 are pressure just above and below the meniscus. Then, so for the concave meniscus, this is the concave meniscus. So this is the pressure above that meniscus. So let's take this P1 and this is a P2. Okay. So this meniscus is formed for this condition. P1 must be greater than P2. Okay. So your correct option is option B for concave meniscus. Excess of pressure inside the liquid drop of radius R and the surface tension T. For the liquid drop, we have the equation for pressure inside. This is equal to 2T upon R. Okay. So correct option is option B. Excess of pressure inside a bubble of radius R and the surface tension. And for the bubble, we have the pressure Pi. This is a 4T upon R. So correct option is option D. Okay. A capillary tube of radius small r can support a liquid of weight 6.28 10 to the power minus 4 Newton. If the surface tension of the liquid is 5 10 to the power minus 2 Newton per meter, the radius of the capillary must be. So what is given? A capillary tube of radius r. So this is the capillary tube. It supports a liquid of weight 6.28. So this is the liquid inside that capillary tube. Okay. And weight, this total weight, this is equal to 6.28 10 to the power minus 4 Newton. So this weight, it is supported due to the surface tension force. So we can write surface tension, this is equal to force upon length. Okay. Now this length L is nothing but capillary tube. Okay. So this total length is nothing is equal to, this is 2 pi r. Okay. And F is nothing but the weight. Okay. So this is the surface tension force will act on perimeter. And this force, it will support this total weight. So put this value in this equation. So this is equal to, this is 6.28 10 to the power minus 4 upon, this is 2 pi into r is 5 10 to the power, sorry, T is 5 10 to the power minus 2 Newton meter. So from this, write the equation for R. So 6.28 upon 2 pi, this will be 1 because 2 pi is 6.28 only. So this is 10 to the power minus 4 upon 5, 10 to the power minus 2. Okay. So 1 by 5, this is a 0.2, 10 to the power minus 2. So 2 10 to the power minus 3 meter. Okay, so correct option is option D. 2 into 10 to the power minus 3 meter. This is the radius. So you should know this equation. So this is a basic equation for surface tension. For capillary tube and the liquid, the length, that is the contact length, is nothing but the perimeter. Okay, so it is a 2 pi r, and here force is nothing but the weight of the liquid. Okay, write down this question. The 5G of water rises in the bore of capillary when it is deep in the water. If the radius of the bore is doubled, then the mass of the water that rises in the capillary above the outside water level. And option is 1.5 G, B 5 G, C 10 G, and D 15 G. Okay. So what is given? The capillary tube is immersed in the water. This is the water level. Okay. And this is the rise of the water in the capillary tube. So this liquid, it has mass 5G. Now suppose initial radius of the bore is r. In this case, water which is raised in the tube, it has mass 5G. Okay, if we double that radius, and suppose this is the rise. So for this liquid, what is the mass? So here radius is 2r. So now we have the formula for rise or fall of the liquid in the capillary tube is, so H is directly proportional, sorry, inversely proportional to the radius. Okay, so you know the formula for capillary rise. So we have H is equal to 2t cos theta upon R rho g. So H is inversely proportional to R. Okay. So we have to use this relation, and we know density is equal to mass upon volume. So mass is equal to density times volume. Now volume here, this is equal to, so volume for the tube, you can consider this is a cross section. Okay. So cross section area into height h. So this is the h. So this is pi r square into h. So h is inversely proportional to the r. So here volume, so we can write this as pi r square. This is 1 upon r. So volume is directly proportional to the r. Okay. Mass is directly proportional to the r. As volume is proportional to the r, mass will be directly proportional to the r. So the ratio m2 upon m1. So here we have the m1 in the first case, second is the m2. So this is equal to r2 upon r1. Okay, so this will give m2 upon m1. So r2 is double of r1. Okay, so this ratio is 2. So m2 is equal to 2m1. So initial mass is 5 g. So second mass will be 2 into 5 g. It is a 10 g. So correct option is option C. Okay. So here m2, this is equal to 2 into 5g. So this is a 10g. So basic equation is H inverse proportional to R. Then mass is equal to density times volume. Okay. So mass is proportional to the volume. Okay. Now volume is area into height. As height is inverse proportional to R, so I will just put the value 1 by R directly. Okay, for the H. So volume becomes proportional to R. So this R square and R get cancelled. Okay. So it is a pi R. So we can write V proportional to R. As V is proportional to R, M is proportional to R. Okay. And then we can write this formula. M2 by M1 is equal to R2 upon R1. Okay. So today we will stop here. In the next class, we will discuss the oscillation chapter. Okay. That is the chapter number 5.